Good morning, everyone, and welcome to our Metabolomics Grand Challenges webinar series. My name is Lloyd Sumner, and today I'm joined by my co-host, Dan Bearden, and our special guest and discussion leader, Dr. Liang Li. This is our 8th webinar in a series, and our topic for today is dynamic range and depth of coverage. We're glad you've joined us, and we look forward to a lively discussion. This webinar is brought to you by the U.S. National Science Foundation Plant, Algae, and Microbial Research Network Coordination Grant and by the Metabolomic Society. As noted, this is our 8th webinar in our series, and we have 2 more to go. You might have noticed that we've had a small break since our last webinar on flux. This has mainly been due to my lab's relocation to the University of Missouri in January. We've now settled in, and it's time to get back to business. You can also see that we have 2 more webinar topics to go on data interpretation and understanding the exposome. So we're still looking for volunteers to host those discussions and to finish out our top 10 webinar series. Before we get going with the science discussions today, we need to visit the logistics. So first, please sign in using your full name. This gives us a good record of who's attending and who's participating in these. Unfortunately, you can only do that when you sign in originally. So if you haven't signed in with your name, please log off and re-log on again using your name. For technical questions, we ask that you enter those in this chat screen down here. And we will try to help you out as we move through this. Dan or I will do this. Unfortunately, Sutanika Ray did not move with us to Missouri, so Dan and I will have to field the technical questions as well. So for the scientific questions, though, we ask that you enter these in the window up here, enter your questions, and raise your hands if you have comments. We'll start the meeting with everybody muted. And as we get to the discussion session, please raise your hand and we will unmute you. The reason for this is if we unmute everybody, the quality of the sound is pretty bad. So this is a way of trying to maintain the quality of sound. So our goals of this webinar series are to present some background information, and typically there's a 15-20 minute discussions, and then to open this up for public discussion and to get feedback. And during this process, we hope to vet and prioritize challenges, discuss these, build community consensus, and then build opportunities for us to join forces to solve or put forward some solutions to these. And so we're scheduled for an hour, but typically these have been going well beyond that, but we will try to close things up at an hour and a half to round out this webinar. So I'd like to introduce our discussion leader today. This is Professor Liang Li. He comes to us from the Department of Chemistry at the University of Alberta in Edmonton, Canada. He's in the chemistry department. He got his PhD in chemistry from the University of Michigan in 1989, working with Professor David Lubman. After that, he then moved to the University of Alberta and joined the university as an assistant professor and has risen through the ranks as full professor and is now chair of the analytical division of the chemistry department. Dr. Li is quite accomplished. He's won many awards that are listed here. He has over 200 publications, and these generally revolve around technology and analytical or bioanalytical mass spectrometry. He's been involved in metabolomics now for many years. He's an editor of many journals, and we look forward to his feedback and his insight. Before we do that, though, Dr. Li has prepared some poll questions. This helps us give a better idea of the opinions of the audience and helps us quantify consensus at this point. So I'm going to hand it over to Dan Bearden, who's going to introduce you to the poll questions, and then Professor Liang Li will join us with his discussion.
It works better if I'm unmuted. So
now I hear you.
Good to see everyone. So there's a series of 10 poll questions, and hopefully we'll get through and get a significant percentage of participation in the first 30 or 40 seconds. So, and I apologize if there's any typos in these. That's fully my responsibility. I got behind in putting these in. So, first poll question. This is to figure out for this audience, which techniques do you most commonly use for metabolomic analysis? So select your poison there, if you would.
So we can see you as you vote, so please vote. We have 86% voted thus far, which is actually pretty good. So keep going, a few more.
All right. It's a smidgen then, so that's good, 86% on that one. All right. Next question is, if you use NMR, what is the typical number of metabolites detected in a metabolomic sample? And I would, Dr. Liang, are you considering these, fully identified or properly identified samples or metabolites?
Oh, just to detect it. Just so we want to see, what is the number of metabolites that people can typically see, and it doesn't have to be identified.
So we're only at 40%, getting close to 50. So please vote. This is an important metric.
Well, that's probably half the audience then is using NMR, I guess.
Ah.
All right. All right, looks like participation has slowed down. That's about a minute, so that's plenty of time. Next question. If you use mass spectrometry, which technique is used most often, greater than 80% of the time in your lab?
That's a tough one because we often do more than one. We often do a GC and an LCMS type of experiment as part of our platform.
Right.
81%, 85, 86, 88, all right.
I guess. All right, so we'll close that in 3, 2, 1. All right, next question. If you use GCMS, what is the typical number of metabolites detected in a metabolomic sample? I hear music.
That's me humming along, so doing the Jeopardy theme song.
All right, leveling off at about 42% participation after a half a minute. So we'll close that poll in 3, 2, 1. Okay. If you use LCMS, what is the typical number of metabolites detected, and specifically not just features, from one run or multiple runs of the same sample?
Again, it's not necessarily identified, just the detected numbers.
So unique metabolites. Is that
Correct.
Yeah, okay.
Right.
Or unique peaks.
Mm-hmm.
Maybe we could do a whole webinar on discussing these questions, and maybe that's what we'll see today. All right, 74% participation, kind of leveled off, so we'll close this poll in 3, 2, 1. All right, next poll question. If you use other techniques, for example, CEMS or some other technique that wasn't on the previous slide, what is the typical number of metabolites detected in a metabolomic sample? All right, it's about 30 seconds into this, and 31% participation.
Yeah, this seems to be a little lower on the numbers here.
Yeah.
It's interesting we've got a significant spread. So, but I think the plan is to review the results after the presentation. Is that correct, Dan?
Yes, Dr. Li wanted to do that.
Okay.
All right, so closing this poll in 3, 2, 1. All right. Now some concentration questions. What do you expect the concentration dynamic range of metabolites to be in human blood? Unfortunately, we normally look at this, so for 1,000 we'd normally have 10 to the 3, but this system doesn't let me do fancy formatting, so dynamic range of 1,000, 100,000, 100 million, or greater than 100 million are the choices.
It's an interesting question. I've heard people cite numbers, but I've never seen a serious prediction of such in the literature, so, at least for plants.
That could be a whole webinar there, probably, I think.
Yes.
All right, so we're approaching almost 80% participation at about a minute. So we'll close this poll in 3, 2, 1. All right, only 3 more questions to go. If you use MS, what is the maximal detection dynamic range of your instruments? Instrument or instruments. So dynamic range, maximum.
Yeah, some interesting answers here too.
Yeah. All right, 30 seconds in, we've got almost 60% participation. So we'll close this poll in 3, 2, 1. 9th question. What is your concentration detection limit for metabolomic analysis?
%54.
Yeah, about 30 seconds.
Yeah.
All right.
People are entering the numbers. It keeps rising though. I wouldn't.
Yeah, people are still. Again, the way that's presented is not the way we normally see it. I can't do a micro symbols. All right, so about 65% participation, and we'll close this poll in 3, 2, 1. All right, last question. So what is your typical sample throughput defined as run-to-run time per sample, including column wash and equilibrium time? So for NMR people, they should participate in this as well, because if you're using automation, you know, like for a one-dimensional spectrum, how much time it takes per sample. So let's include those people too. So, wow, 30 seconds, we've got 70% participation. Oh, we're heading towards 80% participation.
Very good.
All right, so we'll close this question in 3, 2, 1. Okay, and we'll go over those at the end of the Dr. Li's presentation. So I'm going to, if I can find...
Let's switch screens and over to Liang's presentation.
There he is, okay. So I'm going to switch the screen to Dr. Li, and he will begin his presentation. Thank you.
Okay, thank you, Dan. Thank you for this fun questions. Thank you, Lloyd, for the very kind introduction. Good morning, everyone. Thank you for coming to this seminar. My talk will focus on the discussion of dynamic range and the depth of coverage.
Dr. Li, can you show your first slide? I'm not seeing your first slide.
Yeah, me neither.
No, it's, huh? Okay, just 1 second.
You have to show your
So
screen.
right here. on my screen. Just 1 second.
So on your webinar deal, you have to show your screen or to accept the share. So while we're waiting, there we go.
Second.
Just go into presentation mode and you're ready to go. Looks like. I see your mouse.
Okay, good.
Your outline. It's all yours.
Okay, perfect. Okay, so my talk will focus on the discussion of dynamic range and depth of coverage in metabolomic analysis. Set up. Okay, here's the outline of my talk. I will briefly discuss the metabolome analysis techniques and their coverage. I'll talk about the limiting factors on dynamic range and methods to increase the dynamic range. I will end my talk with a brief summary. As we all know, NMR and mass spectrometer are the two main techniques used for metabolomic analysis. Their metabolomic coverage is different. In NMR, quantitative analysis of up to 100 metabolites can be done from a sample without the sample fractionation. In MS, the number of metabolites analyzed is depending on method used. For the more commonly used methods, this is my taking. We'll find out the answers after the talk from all these answers to the questions presented earlier. From my point of view, GCMS covers a few hundred metabolites. LCMS can detect up to a few thousand metabolites. For less commonly used method, direct infusion can detect a few hundred, although in most cases it can detect less than 100. Imaging mass spec detects a few than 100. CEMS detects a few hundred of metabolites in one arm. So far, it appears that the LCMS provides the highest detectability of metabolites, offers the best chance of meeting the grand challenge of metabolomics in high coverage metabolomic analysis. So my talk will focus on LCMS. However, please note that the other techniques are still very useful in their own right for metabolomics research. When we talk about dynamic range for LCMS, let's not forget about the mass detection dynamic range. The upper mass limit is not an issue for metabolomic analysis, as we deal with small molecules in metabolomics. But mass resolution is very important in extending the mass detection dynamic range. The higher the resolution, the better. This is particularly true as we deal with metabolites with their mass distributed within a very small m over z range. High resolution avoids peak overlaps and also makes peak picking easier, thereby increasing the number of metabolites detected. So when we select mass spectrometer for metabolomic analysis, we want an instrument that can achieve high resolution at high spectral acquisition rate to keep up with the ever-increasing chromatographic resolution in order to increase metabolomic coverage. In metabolomic analysis, concentration dynamic range is our major concern. Here we have two concepts. One is quantitative or quantification dynamic range. Another one is the detection dynamic range. In metabolomics, we usually perform relative quantification of metabolites, as a relative quantification information is sufficient for comparative metabolomics, such as measuring metabolite concentration changes in the samples of disease group versus control group. So what concentration dynamic range are we talking about? Let's look at one example. The reference ranges for blood tests in a clinical laboratory. Merck manual provides a lot of information on the reference ranges of many metabolites, also proteins too, in healthy individuals. I also found this chart at the bottom of the slide very useful, showing the reference ranges. At the lower end, we start at 1 picomolar concentration. There are a number of hormones in this very low concentration range. The color bar displays concentration range of a compound, in some cases protein. We then go to nanomolar concentration. Some vitamins and more hormones in the nanomolar concentration range. About 1 micromolar, we have the organic acids and amino acids. We have lots of lipid and some sugar molecules in millimolar concentration. About 10 millimolar, there are some inorganic species. From the reference ranges of compounds in blood, we can make 2 key observations. One is that the absolute concentration of different metabolites range from 1 picomolar concentration to 10 millimolar. Thus, the concentration dynamic range required for detecting all the metabolites is 10 to the 8, or 8 orders of magnitude. The second observation is that the absolute concentration of a given metabolite in healthy individuals has a range of usually less than 10-fold. Thus, the concentration dynamic range required for relative quantification is much narrower. A range of up to, say, 100-fold should be sufficient in most metabolomics applications. Of course, some genetic disease or cell lines with knockout gene for a particular enzyme may have a larger than 100-fold change, but this kind of larger change can be easily spotted in a metabolomic data set. So the dynamic range for relative quantification is not major analytical challenge. So our focus is on improving the detection dynamic range to cover a wide range of concentrations of different metabolites. Typically, one-dimensional LC-MS can cover several thousand-fold of concentration range. In this example, we look at the number of peak pairs of metabolites detected in a carbon-13 and carbon-12 denso-labeled human urine sample obtained by LC-QTOF-MS. These peak pairs are from the metabolites containing amine or phenol group, as benzylation labeling targets these groups of metabolites. Each bar represents the number of peak pairs found within a 2-fold signal intensity range. As we can see from this plot, only a small number of metabolites are found at a very high intensity, and the number of metabolites increases as the signal intensity decreases. If we roughly translate the signal intensity to its corresponding metabolite concentration, we would look at low nanomolar concentration to about 10 micromolar concentration. When the concentration is below 10 nanomolar, in this case, the signal noise ratio of many peaks becomes very low, reducing the number of peaks detected. However, if we just look at the metabolites at the concentration range from 10 nanomolar to 10 micromolar with very good signal noise ratio, we see that the number of metabolites increases as the concentration decreases. If we use a schematic diagram to represent the metabolite concentration distribution in a metabolome sample, it will look like this pyramid. At a very high concentration, there are a few metabolites. As the concentration decreases, we will see a lot more metabolites. So it is very rewarding to increase the dynamic range, particularly by reducing the detection limit. Many more metabolites will be detected as we lower the detection limit. The detection rate, that is the number of metabolite detected per order of magnitude of concentration, increases as the concentration decreases. There are several factors that can affect the lower limit of the dynamic range or the detection limit. These include metabolite concentration. This is an internal factor related to metabolite itself. Ionization efficiency of the metabolite can also limit the detection. This is also an internal factor. The external factors including ion suppression and detecting efficiency. Let's look at these factors one by one. First, metabolite concentration. In LC-MS, we would like to keep the analyte concentration as high as possible. If the amount of starting material is limited, we need to reduce the solution volume in order to keep the concentration high for separation and ionization. This can be done by using nano LC-MS instead of micro LC-MS. For example, with the same amount of injection, in this case, say 5 nanomoles of denso-labeled human sweat sample, micro LC-MS detected about 1,000 peak pairs, while nano LC-MS detected close to 4,000 peak pairs. If the sample amount is not limited, we should inject as much sample as possible to increase the analyte concentration in the sample plug in LC-MS. For example, for denso-labeled human urine at a fixed concentration, when we inject a large volume, hence more sample into LC-MS, we saw an increase in the number of peak pairs detected. However, it leveled off as the injection amount reached a certain point. We usually inject the optimal amount at the point where peak pair number no longer increases. In this way, we can avoid the sample carryover problem. However, when we inject a large amount of sample into LC-MS, signal saturation for the high concentration and easily ionizable molecules may occur. Another issue is that injecting a large amount sample does not overcome the ion suppression effect, as the interference increases their concentration in the sample plug too. It also does not reduce MS peak overlaps with the other ions. To increase the analyte concentration and reduce ion suppression and MS peak overlaps, we can do sample fractionation using an orthogonal or near orthogonal separation method. The additional separation can be performed by using a different mode of column or changing the analyte properties such as changing the pH of the solution or even carrying out chemical derivatization. For example, we can use a reverse phase LC column to separate metabolites, followed by densylation labeling for each fraction, then injecting the densylated fraction into the second dimension reverse phase LC for MS detection. In general, multi-dimensional separation can be performed either online or offline. The additional dimensional separation can separate the interference from the metabolites and simplify the metabolite mixture, thereby reducing ion suppression. It can also concentrate the analytes in a fraction, then load a concentrated fraction onto a second LC to increase the analyzed signals in MS detection. In this example, we detect 1218 peak pairs using one-dimensional LC-MS from this densolated urine sample, and detect 3,564 peak pairs using two-dimensional LC-MS from the same sample. So using multi-dimensional separation in combination with MS detection will certainly increase the dynamic range of detection and metabolomic coverage. Now let's look at the second factor, ionization efficiency. We know that some metabolites can be ionized more efficiently in positive IMO, while other metabolites such as organic acids can be ionized better in negative IMO. So in typical untargeted LC-MS workflow, we use reverse phase LC and hydrophilic interaction LC to supply metabolites with different hydrophobicity and ionic properties, followed by positive ion detection and then negative ion detection to increase the overall coverage. Chemical ion delevatization can be used to increase the ionization efficiency of a metabolite. For example, benzylation can be used to label all the metabolites containing an amine or phenol group and increase their ionization efficiency by 10 to 1,000-fold. So we can use denso labeling to target the analysis of amine and phenol submetabolome. Other labeling reaction can be used to target other chemical groups. And this is a very active research area for increasing detection dynamic range in metabolomics. If we select the labeling reaction or reagent appropriately, we can equalize the ionization efficiency after labeling the metabolites. For the unlabeled metabolites, the ionization efficiency can differ greatly. In this example, after benzylation, this equimol mixture of 22 labeled amines have signal intensities within 1 order of magnitude. So ionization efficiency of these amines becomes similar after benzylation. Next, let's look at the ion suppression effect. Ion suppression is caused by chemical background interference from solvent, salt, buffer, and others. It can also be caused by cool-eluting metabolites in a sample and cool-eluting chemicals such as reagents added to the sample. I already mentioned that we can use additional separation to simplify the mixture to reduce the number of cool-eluting molecules. We should also avoid using chemicals in a workflow that may interfere with ionization. For example, in cellular metabolomics, we may use physical means to lyse the cells instead of using harsh reagents such as surfactant that may interfere with the metabolite detection. We recently reported the use of glass beads with vortex to lyse the cells, followed by metabolite extraction and analysis. Other researchers have reported use of glass beads for breaking the cells. But what we find is that controlling the composition of the cell suspension solution is very important in order to achieve high efficiency of cell lysis. With 50% methanol in water for yeast cells with a very tough cell membranes, we can break more than 95% of cells. No harsh chemicals are used in the workflow. Last, let's look at the factors relating to mass spectrometer detection efficiency. To improve detection efficiency, we need to increase ion transport efficiency, such as optimizing the electrospray tip position, using a large actual size to accept more ions, adjusting ion focusing settings, avoiding collision loss. Some of those actions can be done by the users, and others needed to be done by the manufacturers. Reducing detection noise from detector, amplifier, and the digitizer will also help to increase detection efficiency. In addition, ion mobility separation can help ion detection by removing background ions and separating overlap ion peaks. So there are a number of ways of decreasing the detection limit. So in my humble opinion, with multidimensional separation, it should be possible to detect most of metabolites down to picomolar or lower concentration. However, in reality, we also need to consider the analytical throughput. In metabolomic analysis, there's so much work to do and so little time. We all know that. The metabolomic coverage is also depending on the time and cost associated with the analysis. So when we judge the performance of an analytical method for metabolomic analysis, we want a method that can generate a lot of information about the metabolome at the shortest time. With that, I would like to just end my talk with a summary. I will not read it all, but I would like to just say a few words about the last point. That is point number 10 about metabolite identification. Today's discussion topic is focusing on detection dynamic range, but metabolite identification is another major challenge that we need to address, along with research for increasing coverage. Finally, I would like to thank all members of my research group, past and present, and many, many collaborators for their contributions and hard work. The list of people can be found on my group's website. I would also like to thank the funding agency over the years for their support of my research program. Last but not least, I would like to thank you very much for listening to my talk, and I'm looking forward to having more discussion. Thank you.
All right. Thank you very much, Dr. Li. We appreciate your feedback and your thoughtful insight. Can I ask that maybe you put up your conclusion slide as we begin
Yes.
to work through either the poll questions or through the audience questions? Dan, what did you all agree to do at this point?
I think we wanted to go over the results of the poll questions and see if that generates any discussion. Right now we have just a few questions that have been submitted. So if you have some specific questions and you enter them into the questions window, we'll eventually get to them. And but then if you have questions, you could go ahead and raise your hand using the hand raising tool. And once we go over the poll questions, we'll start addressing those. So,
okay.
All right. So let's look at the poll questions in the same order we took them. First question is, which techniques do you use most commonly for metabolomics analysis? And so it looks like this audience is very heavily MS based, although
so 28% use NMR in solely or with MS.
right. So it's not too discouraging for us guys that do NMR. Any comments, Dr. Li?
No, that's sort of expected somewhere. Yeah. Okay.
Let's go to the next one then. Oops. All right. If you use NMR, what is the typical number of metabolites detected in a sample? Looks like 79% of the folks in total can identify about 100 metabolites. You know, for NMR, we don't count features. We try to match up features to, usually we try to match up features to identify compounds. So maybe this is a slightly different question than one would expect for some of the other modalities. So I'd like to talk to whoever does more than 150. That's pretty impressive. Any comments, Lloyd or Dr. Lee?
I think this is what Dr. Lee had suggested as a number in his presentation, and I think it's consistent. So those that are detecting more peaks, maybe you can comment in the comment screens.
Third question.
Perhaps these people do pre-fractionation.
Yeah, there's a lot of ways that one could increase that number, trading off time or speed for analysis. All right, if you use MS, which technique is used most often, meaning which one technique that you use is used greater than 80% of the time? I think that's a pretty strong signal right there.
Yeah, well, I'm surprised to see such low usage of GC. I mean, we get a lot of information by GC on primary metabolites, or primary metabolism.
All right. And next question. If you use GCMS, what is the typical number of metabolites detected? And here, I guess 77% get up to about 200 metabolites identified or not. So distinct metabolites.
Well, typically we can resolve a couple hundred just in the chromatography domain. Then if you add deconvolution, you can boost that quite a bit depending upon your sensitivities. You start getting into a point where you get a lot more noise as you start pushing the sensitivity of the deconvolution, but I think those are very reasonable numbers. So 1 to 200 in the chromatography domain plus deconvolution can probably double that.
Mm-hmm.
Any other comments, Dr. Lee?
Nope.
All right. If you use LCMS, what is the typical number of metabolites, not features, from one run or multiple runs of the sample? Looks like the number goes up a little bit for this, well, not a little bit, up to 600. So about what, almost 60% of the folks say they can get up to 600 metabolites. Significantly, it looks to me 26% are saying they're seeing more than 1,000 distinct metabolites. So,
Mm-hmm. Yeah, if they use different modes of separation.
right.
Mm-hmm.
Different
And also,
ionization modes, yeah.
correct, that's right. That seems to be starting to become a more common platform for increase the coverage for on-target analysis. You know, just switch different column and changing the modes of ionization is not that difficult. Of course, it takes a longer time too. So.
Right. It's I guess it's usually a trade-off of time versus information, right? All right. If you use other techniques, mainly we were talking about CEMS or direct injection or something like that, what is the typical number of metabolites detected in a metabolomic sample? So, yeah, heavily weighted to less than 100, but some people, again, you'd have to dissect this response maybe to see if some of the distinctions between what people are using. So, any comments, Lloyd or Dr. Lee?
Mm-hmm.
All right. Next one, what do you expect the concentration dynamic range of metabolites in human blood? I guess most people, the mode of this is 100,000 dynamic range, or 10 to the 5. 30% of the people said 10 to the 8. And I believe your presentation indicated you felt it was 10 to the 8, Dr. Li, right?
That's yeah.
But those are known metabolites, right? It is conceivable that there may be other unknowns at lower concentration. So 10 to the 8th is substantial. I've heard other quotes of, 10 to the 12th or so. But I think the bottom line is that the in vivo concentration dynamic range far exceeds that of our instrumentation.
Right. I guess I would ask, when do you go from the metabolome to the things like hormone and things like that, which I don't know. I always wonder where the metabolome stops, but maybe that's another discussion.
Well, I generally consider hormones small molecules and part of the metabolome.
Yeah, some nice work done in target analysis of those hormones.
Right, right. If you use them as what is a maximal detection dynamic range of your instruments. So it looks like the mode is most people are getting up to about 100,000 in dynamic range, so five orders of magnitude.
Which I think is reasonable, 10 to the 4th, 10 to the 5th. So 10 to the 5th is pushing it, though, from my experience. We would like to hear from those that are pushing over 100,000 dynamic range and how you're doing that. Is it a targeted method, or are you doing other tricks such as those that Dr. Li presented?
Okay, so this is Oliver Fien here. Of course, some triple quadruples can get more than 5 orders of magnitude dynamic range.
Okay. That's correct. That's what I actually wanted to say. If you do the target analysis, that's obviously is possible. But I think we're discussing here is more of trying to cover all the compounds, not particularly focusing on the target analysis at this point.
No, the question as raised is, I mean, many of those questions, sorry to intervene here, many of these questions are not specific enough to get a meaningful answer. And I made multiple comments now online, because there's too many comments. But I think these questions should be more specific next time, or vetted by maybe the group of organizers.
Well, we appreciate your feedback, Oliver.
Yeah, that's right. No, I think it's also important that we realize that we just want to get a survey of what rough number of metabolites that people can detect. If we want to do a protocol, so we can define the question and also more specifically focusing on a particular technology. Because within one technology, there's a lot of variety of different ways to look at it.
All right, let's go. What is your concentration detection limit for metabolomic analysis? That's spread out fairly wide, I would say. Broader distribution than some of the other results we had. All right. So it looks like the mode of that is 10 nano to 100 or 100 nano to 10 nanomolar concentration. So, all right. And then finally, the last question: what is your typical sample throughput, defined as run-to-run time per sample, including column wash equilibrium time if used? Again, that's kind of almost fairly flat distribution, it looks like to me, but maybe the mode is about 20 to 30 minutes for a run per sample, and that would make sense for NMR as well.
Well, we often make a value-based decision upon, separation efficiencies. And in that we are willing to spend a little bit more time if we get more peaks in the separation, or more resolved peaks. But I think most of our protocols are kind of in the middle of that range, 20 to 30 minutes.
All right. Well, so
Okay, so that's the results of the polls. We can now turn to some audience questions. We have a few. Oliver's got some that he would like to ask. And the first one concerning derivatization. Oliver, would you like to voice that question?
Yeah, Liang Li is a long tradition on danzolation. I wonder how many other people use danzolation.
There are about 5 groups right now adopting the protocols, and we've been helping them to do that. The important thing is not just doing the danzolation chemistry, but the data processing is totally different from typical on-target, underivatized metabolome analysis. So that part is it needs a little bit help. And also the library for compound identification, and we start to now having public library of denso-related standards available on the website, so people can do the identification. Because in the end, when you detect a lot of peaks, if you can identify them, then cannot tie it up with the biology and the clinical information. So those are these 2 things: database for metabolite ID, and also the software for processing those labeled isotope labeled metabolites are the primary focus on research, and I think it's getting there.
So outside of danzolation, are there other groups using other reagents for derivatization?
That's right. So very good. Actually, there are about 20 research groups active working on various different labeling reactions, labeling chemistries.
Well, one of the primary reasons for doing LC is to avoid the derivatization necessary for GC. What are your thoughts on the value gained by that? I mean, you talked a little bit about it, or, giving you better sensitivity or reducing background effects.
Yeah, that's right. So the what I see the derivatization is a way to improve the detection. So how else we can actually increase the ionization efficiency, for instance. And through the derivatization, we can change the chemophysical property, make them a little bit easier to find in the ESI. Now, the problem is, of course, associated with derivatization reaction. And people think, yeah, like what you just point out, that when we're doing LCMS, we're just trying to avoid derivatization, right? But keep in mind that when we're doing derivatization, the chemical derivatization is just one of the steps in the workflow. When we have to do protein precipitation, right? If you're dealing with blood samples, we have to do a lot of extraction experiments. Those are all chemical manipulation or physical manipulation of the entire process. So when we're doing derivatization, if the derivatization method is very robust, very simple, very quick to do, so adding that step is not necessary will actually prolong the process or make it the analytical difficult.
Okay. Oliver, any other comments or questions before you have to take off?
Well, I think this the number of peaks detected that Dr. Li showed is totally dependent on the definition of a peak, of a feature. What do people count as a peak? What do people count as a metabolite? Going back to the polls, but also to the slide he showed. And I think it very much depends on the software you use, background subtraction you use, signal to noise you choose. I think the question, as has been shown, is a bit misleading. Because you can get easily thousands of peaks even in, say, GCMS, and I'm sure in other samples as well, if you choose to go for lower signal to noise ratios, or if you overload or saturate your detector. So it all comes down to the point what kind of instrument you have, what is the dynamic range of your instrument under practical conditions, and you know what is a peak and what is an identified metabolite, and we have discussed these questions in other grand challenges pretty thoroughly, I think.
Yeah.
So for those who are on the line, have followed those grand challenges, they would understand that, this is all field in motion in a way. So I wouldn't give too much on those numbers, to be honest.
No, I actually, what I feel here is that, no, I fully agree, because there's a lot of discussion about the number of peaks seen and the features. That's why in the question, we're not talking about just the features, right? So there's some algorithms that are starting to come out to filter those data in order to just extract the metabolite information. But from my point of view, I feel that if we use the feature, whatever the data you have, search the current metabolome database, not the synthetic compound, just the metabolome database, to see just the mass match, accurate mass match to what kind of match, number of matches you have. Those matched one, I feel that you have a better confidence in the existing of those metabolites in the sample.
Yeah, I politely disagree. You cannot take a mass and match it to a database. I mean, 15 years ago, 10 years ago, we have already had the discussion. You have a potential hit, but this potential hit doesn't mean anything unless you have further evidence. And we have published minimum standards in metabolite annotation 10 years ago, where we said you need 2 orthogonal parameters that give you some sort of confidence that a named metabolite is actually what you think it is. And the match in a database, it's depends on the database how large it is. You get more matches or lower matches. This is you need more than one parameter for identification or annotation.
Oh, absolutely, absolutely. But at least you can see that the features you find, for instance, sorting added ions, you can when you're doing the match to the mass database, you immediately say, this is basically 22,000, from the other peaks. So these two are actually supposedly belong to the same metabolite. Yeah, that's the point I want to make.
Correct. That's deconvolution.
Yeah.
And that's correct. You need to have a software that does deconvolutions, so then you don't do double counting for in-source fragmentation or adducts and so on. Absolutely. Absolutely.
So the take-home message is that peak numbering and actually quantifying the number of detectable metabolites in our profiles is still somewhat questionable. And I think as we improve our instrumentation and our informatics, that maybe that question will get greater specificity in answers. Okay.
Yes.
All right. So moving along, we have another question by Jun Min Ping. I'm going to unmute you, Jun Min, if you would like to ask your question. All right, Jun Min, are you prepared to ask your question? Okay. So just asking it for them, could you estimate the dynamic range of the metabolome in a cell culture? Is that different than what we might see in plasma or urine or other tissues? So that question is to you, Liang.
Oh, okay. So yeah. So it's interesting that in the cell, when we're doing the densilation labeling to the experiment, and we actually see a lot of peak pairs. And again, getting back to the uniqueness of those peak pairs, so we find it to be unique in terms of retention time and mass. And in our peak pair picking, we filter out all these sodium peak, potassium peak, dimers, trimers, and potential fragment lines. So that's in the software building. The issue with the cell extra dynamic range is that there are potentially many intermediate metabolites within a pathway that perhaps being captured by using a sensitive technique where other technologies in the past may miss it. So it's a potential that there will be a lot more in the metabolites in the cell. Now, what we observe in others too, there's a lot of oxidized species when the cell is under stress. For instance, the lysine chain. The lysine chain is CH2, so there's a high number of oxidation happening in this chain. It's like the fatty acid. You have to oxidize fatty acid on, on oxidized stress. So those are species that I think those are relatively new species perhaps will be discovered in the future as we dig a lot deeper into the metabolome of the cells. And I really don't know what is the concentration dynamic range of a cell at stress. But it seems to us we actually have the same kind of pyramid shape of distribution. As we dig deeper, we see more metabolites.
Mm-hmm. Okay. Mm-hmm. So our next question comes from Bo Zhang. Bo, I've unmuted you if you would like to ask your question. Okay. No comments. Actually, it was his question was asking about the 150 metabolites using NMR. So if you can identify more than that, could you please post to the questions and tell us how you're doing that? So, sorry. The next question is from, let me see, Liang Li. Let me scroll down here and unmute him or her. Liang, are you there?
Yes. Oh, no, not me.
Oh, Liang Zhao.
Okay.
There he is. Would you please ask your question to Professor Li?
Yes. First, I would like to thank for the wonderful presentation, Dr. Li. My question is regarding the dilation. I'm just wondering if you have done some calculation because dilation basically works only with metabolite with amine function group.
Correct.
I'm just wondering if you use CAC database, what the estimated percentage of those metabolite that containing the amine function group compared to the whole metabolome?
That's actually a very good question. About 40% of non-metabolite in all different pathways contains amine group. So the question here is whether we can detect all this. Well, what we find is that when we use one-dimensional LC, it's difficult to cover all. However, I think in the future, when we do a two-dimensional LC, we have a potential to cover. In the current dental library, 275 amines, mainly amines, some phenols. It covers about 43 metabolic pathways, but not all the amines in a particular pathway are actually covered. That's because the lack of chemical standards for those compounds. But we are working towards trying to resolve these issues. This is, I think, as I point out, the summary, my point 10, that is the metabolite identification, should be go along with the increase in coverage. We can detect a lot of peaks, but if we cannot identify the peaks detected, it's not very, very useful. Thank you for the question.
Okay. So Justin Vanderhooft had several questions and comments. Justin, I've unmuted you, and you're welcome to ask your questions and or provide your comments.
Well, thanks, Lloyd. Thanks, Lee, for giving your talk. Well, I just a lot of questions, so I won't go over all of them, so it will take too long, but feel free to use them in next webinars or take them on board for whatever goal you have with it further on. But, so, regarding the derivatization, I think my main question would be, like in every step we add to the whole workflow, there's a risk that we treat metabolites differently, and I know that we also do that with extraction and with and some other steps, but that's just one command and one thing that I think we always have to keep in the back of our mind. Some metabolites might not get derivatized, and then we won't see them anymore. But I think more interesting questions in terms of coverage would be, do many groups use ways to concentrate the samples prior to injection or analysis, for example, solid phase extraction or other ways? And do we expect any major or large breakthroughs in the nearby future in terms of the coverage?
And that's an excellent comment and a very good question. On the comments of chemical derivatization process, I think yes, there will be issues associated with it and complications associated with it. This is one way to increase the coverage, and I hope more people will start to address some of the issues. Well, on the question in terms of optimize the workflow, particularly with regarding to the, say, the injection amount to a mass spectrometer. We all know that the mass spec is a very expensive device. So when we do injection, we try to optimize the amount of sample injected into mass spec so that we can take advantage of all the capability of mass spec can offer to generate the high coverage. The question is always like how you can actually quantify the metabolites before you do the injection. In proteomics, we use simple lots of kits that are available to do quantification, and we always inject either digest or protein for the proteomics work. In metabolites, because they have a diverse chemical physical properties, so how we can address quantification issue. So I would like to hear other people's opinion about it. But let me just tell you what we do. In our case, when we're doing untargeted metabolomic work, that is unlabeled, use the 2 columns, 2 annulation, we always do a quantification of the metabolome samples first. That's because we want to do the sample normalization first. So the way we're doing is we use, again, the degradation chemistry. It's so simple to perform. So we just use the UV peaks intensity as the criteria for quantification of the amount or concentration of the labeled metabolites. Use this amount of labeled metabolites as surrogate indicator for the total concentration of metabolites. We use that as a normalization as well as optimizing the amount of sample injected into LCMS. So I'd like to hear from the other peoples here how people actually do quantification. Do you do quantification before you inject the sample into the LCMS?
Well, we're actually working on some experiments now with some other plant researchers looking at phloem sap, and the steady state level of sucrose in the phloem is pretty consistent. So we're actually quantifying sucrose and then normalizing to that as a way of, if you will, quantifying the metabolome and normalization as you discussed.
Oh, that's great. For urines, people use quantitating all the time. Yeah. Mm-hmm. Yeah.
Okay.
Yeah, I mean, just to add, in classical polyomics, we have a bunch of different samples, and I think in some cases it's just very hard to normalize on something, because first you need to understand what's in there. I mean, yes, for urine and for some other samples you might argue we know enough now that we can start to use some metabolites as normalizer, but this is not always very easy, I think.
Well, I agree that there are caveats to doing such, and there are concerns, but I kind of like Liang's idea of doing, for example, a UV spectra. So plants have a lot of phenolics, and if you just normalize to the UV absorption at a certain or across several wavelengths, that might be a way of doing it in more of a non-biased type of approach.
Oh, sure. Especially in that case, because you cover a lot of metabolites and classes if you choose the right wavelength.
Yeah, so they have near IR methods that are kind of used to do various types of analyses, and they do training sets, and so maybe that's another quick way of normalizing. Okay. All right, we have another question from Daniel Gaucher. Daniel, I'm going to unmute you. You're unmute if you'd like to ask your question about carbohydrates.
But thank you. Can you hear me?
Yes.
Yes.
Yes, okay. So my question was, of course, you have those micromolar to millimolar to micromolar metabolites that clubbered your chromatography and cover so many other interesting features. And in plant, at least, most of them are sugars. I mean, they're carbohydrates. They're all over the place. They're in very high concentration. And usually we are limited in the amount of samples we can inject because we just destroy our source and the sensitivity. So do we have any methods out there to remove carbohydrates selectively and leave the other metabolites there?
That's we have an expert always working on plant metabolomics, but I just want to point out that sugars usually is a very kind of a hydrophilic, so perhaps you can do solid phase extraction of the metabolites and wash it all the sugars out. But in the plants, my understanding is a lot of polyphenols. Those are all captured in the SPE2 that can suppress your signals. Lloyd?
Well, I can easily visualize a way of doing it where you used some type of reverse phase, solid phase extraction. Sugars are very polar and they would come out in an aqueous wash. And you could then elute the rest to get a better picture. And yes, I think that would increase your dynamic range for other molecules. And I've seen similar methods for defatting or delipidizing samples as well. I know there's been some work with ethanol type of extractions in plants, usually more to enrich in sugars, but if you would do an ethanol extraction first, then come back and re-extract the remaining, that might help as well. So does that answer your question or give you an idea? Yeah, I think it's a good suggestion.
It does give me an idea. Yeah. It does give me an idea of multiplying the number of samples.
Okay. Yeah. Well, yes, it makes more. So it's yeah, that's the challenge, right? So fractionation though does give us more coverage, and if we want more coverage, then right now that's the way to do it. Or maybe in the future there may be online ways or multi-dimensional methods, LC type of things that don't use ion exchange, but maybe some type of Hillick reverse phase or type of separations. And I'm looking forward to some of that technology coming online. All right. Well, I appreciate everybody's questions and comments. Dan, I think we've made it through most of those. Did I miss anything?
No, I think we had some quite a number of people who interacted numerous times. I did see that Bose Zhang came back online for a moment. I don't know if he's still there. I don't see his name anymore.
I don't see it either, and it says he's left here, so okay.
So, other than that, if anybody has a last moment question, if you would raise your hand, and we will give you a couple of seconds to do that if something's sprung to mind.
I'm running up and down.
I don't see any hands going up. We're down to a much smaller number of attendees, so I think we're done, Lloyd.
All right. So, well, Dr. Li, I'd like to thank you again for your contribution and your insight. We appreciate that, and thank you again. So, with that, I'd like to bring things to close. Well, before I close, do you have any other final comments, Dr. Li?
No. I think it was a wonderful discussion, and I hope I just brings more questions to the audience and the community. And
Yes.
hopefully we will address some of those questions and challenges in the future.
Yes. Well, thank you again. I think you did a great job, and I appreciate it, especially the dynamic range calculations in vivo or predictions. So with that, it brings us to a close. We have recorded this webinar. It will eventually be available through our Plant, Algae, and Microbial Metabolomics Coordination Network site, and also through the Metabolomic Society. So thank you again for your time and your input, and we bring things to a close.